All right, let's see if we can try this again. Okay, now nobody is watching this broadcast right now because really what happened is about an hour and a half ago, I created the original broadcast and I had forgotten to put on all the graphics. Okay, so in order to make better, I'm going to do is redisplay the same lecture, and I'm probably going to go and remove the old lecture, and I'm going to put this one up here instead, and this one is going to have the graphics guaranteed. Yeah, so this week, what we're going to actually talk about is the rendering equation. Now, the rendering equation is the actual segue between physically based rendering and PBR and so forth. And so if you have any questions or you have any concerns, please contact the YouTube or check out TechArt.edu and email Chris at techartedu.com and tell me what you're thinking. And hopefully we won't have any more confusion. But I'm going to go ahead and update all of this on the website this evening. So without further ado, let's get this show back on the road and let's go ahead and create the rendering equation. Okay, so here we go. Yes, okay. We now see the rendering equation and we now see actually what's going on here. Okay, cool. You're probably going, okay, what is the rendering equation? Well, last week we gave a quick introduction about physically based rendering. And physically based rendering is awesome because it's the key of creating photorealistic images. And companies like Epic and Unity have been able to get the real-time engines in order to display physically based rendering in real time, which is really looking awesome. So you have photorealistic images going off in real time. Now, they use a bunch of light maps and shadow maps and other kind of pre-processing in order to do a lot of the heavy lifting kind of before the game actually starts. And that's what enables this PBR stuff to happen in real time because most of the pre-computing has happened real time or has happened before the actual playtime. Now, on the other hand, we've got ray tracing. Now, ray tracing is amazing, and it is the next phase of photorealism because it's coming down the pipeline. And as soon as the new generations hit, new console generations hit, I guess it's hitting right now, the new PlayStation 5 and the new Xbox station, you're going to see all a bunch of this crazy stuff here. But we're going to show this. Okay. And now rail chasing, I didn't think this would happen during my lifetime because like back in the 80s when I first introduced ray tracing, I said, oh, this is never going to happen. This is just too crazy. It's just too expensive. It would never happen in real time. But lo and behold, here we are. It is year 2020 and we have real-time ray tracing. And real-time ray tracing is coming down for everyone and everything's going to make the transition. And so how do we make the transition from PBR to ray tracing? And we start by looking at what is known as the rendering equation. The rendering equation is the segue from PBR to ray tracing. So probably I was going like, all right, I know rendering. That's like the old Illumination model, right? With the old traditional Phong stuff. We talked a little bit about this last week, where you've got your surface normal, and then you've got your incident light ray coming in as a golden ray, and then you have a reflected ray coming out there and a viewpoint coming off there. And we all know about that. This is the standard formula that we've used for years and years and years. The red equation is what is the ambient light or what the color of shadow is. The green is the Lambert equation or what is the amount of lighting the surface actually receives directly from the light itself. And the more perpendicular the light is to the surface normal, that means the less light it's going to receive. And then you have the blue, which is the specular component. And the specular component gives that bright hot spot. And that is dependent not only on the angle of the light hitting the surface, but also the angle of the camera looking at it. So we've got the ambient and the diffuse, and the specular equals the intensity of the pixel we're currently looking at. Guess what? That was the old Illumination model, no longer valid anymore. We've got something brand new, and we have called the illumination or the rendering equation. All right, let me tell you a little bit about the philosophy first. Now, this is all based on the law of conservation of energy. And where the conservation of energy says that it's the total amount of energy of light emitted from a point And oh yeah, there's the point X in there. Along a particular viewing direction, then we have the viewing direction. Yeah, there we go. There's their viewing direction. Okay, this is it's actually a sum of the incoming light to the surface and a BRDF. Now, all those little yellow arrows, that's the light coming in from all sorts of angles onto our point X. Okay, in other simpler terms, this is what it looks like. So in other words, on the left-hand side, we've got the color of the pixel we're actually looking at, and it equals the light actually being emitted from that point X plus all of the light that the point X is reflecting. And so we have reflecting, emitting equals the actual light that we see here. And so this statement actually says that the light leaving point X on a surface I in the direction of omega 0 is the sum of all the light emitted by and reflected by the surface along omega 0 from the small area around X. So in other words, remember, the light that we see on X is the sum of the emitted light and the grand sum of all the other lights that are reflected off of point X. Okay, in its glory, this is the full rendering equation. Now, this bestial thing is a bear, and there's a lot to do with this. And I'm going to explain why it is challenging, but I'm also going to explain how we are about to decompose this and actually make it a lot easier. So if we take a look at the things component by component, it will start to begin to make sense. Now, X is the point on the scene. X is what on the left-hand side of the equation, X is the value that we're actually solving for. The light, okay, it equals the sum of X, the color of the light given off to it, and then we've got all this crazy mathematical gobbledygook on the other side. Now, I have to admit, that scares me. Okay, but on the other side there, we have omega I, and that means all of the light incoming from some other direction. You mean not the light coming from the camera itself, but all the light coming in from around the world and hitting that point X. Okay, W0 is the light that's just coming from that point directly towards the camera. Okay, N, that's the surface normal. Now we've seen that before. That is the kind of like a little arrow that sticks out perpendicular from the surface that we are rendering. And then here we have this squiggly thing. Now for those of you folks who understand calculus, you recognize what this is, and that means this is the integral. And it's a two-dimensional integral, so it is not only over one dimension, but it is of two dimensions. And really what this is you've got this fancy, complicated formula on the other side of this integral, and we're going to do that over and over and over again, potentially thousands of times, in order to figure out what is the impact of light hitting this object from all different angles. Okay, let's take a look at it a little bit more simple. The first term is what kind of light do I see at the point X? You know, how much light do I actually see? And it equals, it's the combination of the amount of light given off by point X and the amount of light that is reflected from point X. And so there's the second term, is how much light does the point seen giving off? How much light does it actually give off? Now the third term is this big old integral. And this is the sum of all the light coming into that point from all angles. In other words, this is all light that is reflected off of that point. Now inside of this integral, there are three other terms that we need to worry about. The first term is how much light is actually incoming in from the surface. The second term is kind of pretty much important, because this is like the guts and the heart of the whole equation, is the BRDF. This is the material function. And in other words, is that light behaves differently on different materials. So therefore, rubber looks like rubber because of certain properties of the material. Leather looks like leather. Skin looks like skin. all these different factors and they all have different BRDFs. And this is the traditional physically based component that makes it physically based, because this actually duplicates what light is doing when it bounces off the surface. And then we have this third term, which you might recognize, and that is the from the angle coming in to the normal. This is like the good old Lambert formula. We've seen this before. This is from the Fung equation, and so it's really just the same thing. But instead of a specific light, this is with all the light sources. Okay, so when we're talking about all the light sources, what are we talking about? All right, so let's take a look at this stuff inside of the integral. And so this whole kind of like S squared and then the delta gamma I, what does this all mean? That means that we are going to consider all possible light coming in from all specific directions onto this. And we're going to use this in two dimensions. And one is the zenith angle, which is kind of like the angle that, if we were to have this thing, the angle goes up and down, that's the zenith angle. And then the azimuth angle is the angle that kind of pivots around there. So this is two dimensions creating this huge wide sweeping pan. And this actually is what we're doing. This is why it's S squared, because it's two dimensions. And this is the overall directions of where the lights are coming from. All right, now let's talk about the BRDF. Now this is the bidirectional reflectance distribution function. What a mouthful. Okay, now this is the function that describes what those angles mean to the material when light hits it at those specific angles. Now, for all of the azimuths and all of the zeniths, it has some kind of value. It shows how many photons and how many electrons and how much light is given off from the surface depending on the angle. And here's the properties of what these BRDF has. When energy comes off of point X, that's called the radiance, because that from point X, it's radiating light energy out. But what comes into the point X is called the irradiance. And in order to make one of these functions actually work, it's got to be doing one thing. It's got to conserve energy, which means is that the light energy coming into the point has got to equal the light energy coming out of the point. So it's got to go back and forth. So the incoming and the outcoming light rays are considered reversals of each other. And you can't affect the overall outcome. So that the BRDF has to balance and juggle everything so that the amount coming in equals the amount coming out. Now, where do you get these? Well, you could get them, like some researchers, you can approximate them, but a lot of researchers have spent a lot of time and they actually measured what various materials look like and how do they behave with various light angles to it. And these are some good websites to check out various BRDFs, because they store all of the properties like this. Now, most of the real-time rendering engines that have PBR actually employ a lot of these BRDFs within them, so they have most of these functions. There's not a whole lot of them, but here's a good place for them. Now, if you really had the resources and if you found some kind of crazy material came from a meteorite that came from the dog star somewhere along the way, I don't know where this thing came from, but you wanted to test that, you would use an apparatus that looks kind of like this critter. Now, they put the material that they want to check out inside of the center of the big donut there. And then they have this big old arch that kind of right over it. And what this has is a light source and it's got a sensor. And so what they're doing is they're pointing at the object and they're testing as the light source moves up and down around the angle, then the sensor picks up like how much light is actually being reflected from the object. And this arch, once it does a pass going over 180 degrees around, then it turns just a little bit, and then it does it all over again, and then it turns. It does all these. So really, it's picking up a buku of data, and so that's why we're learning about all S squared of about the azimuth and the zenith angles, and there's a lot of them. All right, so if there's a lot of these angles, an infinite number, actually. How do we actually figure this out? Well, we use a concept called importance sampling in order to narrow down what information and what light do we really want to consider? Because, obviously, if we're going to do for every possible zenith and every possible azimuth, then that's just way too much. We'd never get an image out of this. Okay, we use the varying sampling depending. It depends on the behavior of the BSDF, or in this case, it's called a bidirectional scattering distribution function, and the angle at which we're going at. Now, this is important because different materials behave differently and they reflect light a little bit differently. Let's show for an example here. If we have a light bouncing off of a mirror, then it kind of like the reflection equals exactly what was incoming. So the incidence equals reflection and we are good to go. That's nice and simple. But as we start to get more glossy, then the light beam hits the surface and it kind of bounces and it kind of spreads. Now, as we get to more diffuse matte objects, then it hits it and it just, boom, the light explodes all over the place. And so that's why you got to keep track of how smooth the object is, or what kind of, is the object metal? Is it going to reflect like kind of a mirror, or is it going to be glossy, or is it diffuse? Is it going to be rough? Is it going to be smooth? These are super important factors because they all manipulate how the BRDF behaves inside of the rendering equation. So if we take under consideration the BRDF and the angle, then we also are going to do is take into consideration the lighting. Because if you know where the light is, then you know that you can look in fewer places. If you just focus your rendering equation at your available lights, then you know that you've got the good stuff. Okay, so why not just target your known lightings? I mean, the lighting environment, they knows where all the lights are, right? So why not just go ahead and focus in all of the lights? So once again, we've got our mirror reflections, and then we can focus right from the mirror reflection onto our desired light there. And likewise with the glossy surface, you'll see that there is a lot of overlap there between the glossy surface and what's being reflected. And so there's a good portion of what is being reflected from the glossy surface coming in from the light itself. And then once we hit the diffuse material, then there's going to be its amount that is reflected, only a portion of it actually corresponds to the exact light it has here. So your diffuse mats are going to actually have a lot to consider. Okay, now if we're going to use this concept of multiple importance sampling, we can actually test and see with this. This is a classic test of where, like on the left, you have the sample light source, and then on the middle, you have the regular BRDF. But when you use this multiple importance sampling in order to selectively choose where you're sampling the azimuth and the zenith angles from, then you're getting much better results and you ending up with everything looking really good. All right, so that pretty much is a recap of what we went over earlier today, but with all the graphics. Okay, now if you want to see more about this stuff, you want to get more information, go ahead and check out the new website, which is techartedu.com. Go ahead and sign up for all of our updates because we're going to have lots of updates flowing here, kind of like this situation, and we're going to email you what all these updates are. So go ahead and sign up for it. And if you want to, just go ahead and check me out on Facebook and on LinkedIn. That's Chris Rhoda. And also, if you like what you see, go ahead and subscribe to this YouTube channel. Okay, now we aren't going to have a lecture next week because it's a Thanksgiving week, but in 2 weekends, we're going to have, 2 weeks, we're going to have a 2 lecture session just on ray tracing by itself. Now, ray tracing is going to be a big subject, and it's going to be even bigger, and it's going to manipulate how we do computer graphics in the near future. So for all you artists and you tech artists out there, you got to know your ray tracing and know what to expect what's coming down the pipeline. All right, thank you very much for coming today. Thank you very much for your patience dealing with all the technical difficulties, and we will see you all again in a couple weeks. Until then, have a great Thanksgiving. Ciao.